session. So it's my pleasure to introduce Yasu Kawahigashi from Tokyo. And he's talking about the relative Drinfeld commutant and alpha-induction.
So I wanted to thank the organizers for the invitation to speak here. Then I realized that I'm listed as one of the organizers. But I didn't do any organization work. So I thank the real organizers for the invitation. So today I'd like to talk about something related to the quantum double in the setting of subfactor theory. So I start with some rather old classical work on quantum double in the setting of subfactors, originally due to Okunian, and also we follow the formulation of Izumi. Also called the Drinfeld center. So we start with fusion category C. And everything is unitary. So this is an abstract notion, but if you are not familiar with the notion of fusion category, we can think it as a finite set of irreducible MM bimodules, which is closed under the conjugation and the relative tensor product operation up to isomorphism and taking direct sum. So where say M is a type 2-1 factor or also type 3 factor. In that case, we can also use the sector machinery of Longo. So in this setting, in this general setting, in general, we have no relation between X tensor Y and Y tensor X. So they are not commutative in general at all. But then there is a general machinery to produce certain commutativity automatically. So you actually braid it. And actually, this is a non-degenerate braiding. So this is so-called modular tensor category. So there is a general machinery to produce a modular tensor category from a given fusion category. And so this construction is called the quantum double construction or the Drinfeld center construction. We have three different formulations. So we have okay. Or equivalent. So the first So the first construction is based on the asymptotic inclusion of Okuniano. So it's purely subfactor technique. And actually we use the formulation due to Longo-Rehren. So this is a given factor for which we have finitely many MM bimodules. Then we take an opposite algebra where the product operation is reversed. Then we have this subfactor where the larger factor M regarded as M tensor M opposite bimodule. This has a decomposition. So and this is lambda is in the original fusion category C, and actually irreducible object or simple object of the fusion category. So there is a canonical construction which produces this decomposition. So we have a construction of such a subfactor. Then, so first we construct a new subfactor, which is of this form, then we can look at the R bimodules arising from this subfactor. Then, well, from this description, it's not trivial at all, but it turns out that here we have braiding, which is non-degenerate. So R bimodules have a commutative tensor product. This is one construction. And the second, so this was mostly studied by Oknianu. And the second one is a formulation due to Izumi, so half-braiding. So we look at the sigma, which is an object of this category, fusion category C, which is possibly reducible. Okay, we do not assume irreducibility here. Then half-braiding is of this form. So this kind of graphical expression is common in this kind of study. And if you are not familiar with this kind of thing, I just simply say, so this such a triple point or crossing means an intertwiner. For example, here we have, for beta, they are irreducible object in C. So here, this crossing means we have sigma 10. Okay, my convention is that we look at this diagram from the top to the bottom. Okay, some people use the opposite convention, but my convention is from the top to the bottom. So here we have sigma tensor beta 1, and here we switch the order. So here, this is an intertwiner from sigma tensor beta 1 to beta 1 tensor sigma. Okay, and this is an intertwiner from beta 1 to beta 2 tensor beta 3. And this is a composition of two intertwiners. Here we have three crossing or triple points. So here we have one intertwiner here, another here, another here, and this is a composition of three intertwiners. So this equality means that the composition of the three intertwiners on the left-hand side is equal to the composition of the two intertwiners on the right-hand side. So this, if we do have a systematic choice of such an intertwiner for any crossing of sigma with respect to beta, this is called a half-braiding, because this kind of thing is really like a braiding structure. Then sigma with half-braiding then this pair, this gives braided tensor category. So this is the second formulation, and we know that it's equivalent to the first formulation. The third formulation, which is due to Okniano, is the following. This is based on topological quantum field theory of dimension 3. So we have notion of tube algebra. So this is finite dimensional fifth algebra. And as a linear space, this is just a direct sum of the intertwiner space of from lambda tensor mu to mu tensor sigma. So, or maybe I should use mu, sorry, mu here. And graphically, this kind of intertwiner space is represented as this kind of square, whether all the four edges are labeled with irreducible objects or bimodules. Then this here we have 4 edges labeled by modules, but the top edge and the bottom edge, they are labeled with the same thing. So we have a picture of square, but the top edge and the bottom edge are identified. In this way, we can fold this picture, then we get the picture of a tube. And this is why we call it the tube algebra. And then the product is basically a concatenation. Up to some interpretation. And also the star operation is a certain reflection. So this is a finite dimensional fifth algebra. Then minimal we look at the minimal central projection or direct summand of this finite dimensional fifth algebra. Then we do have category. So they are objects of a new category, braided. Okay. So these three are the same thing of the quantum double construction. So in each way we can look at the new tensor category new tensor category. Okay. So that's a classical thing which has been studied for more than 25 years. Then today I'd like to talk about the relative version of this one. So this is a quantum double construction, but that's also called the Drinfeld center construction, as I wrote here. So it's a kind of center in some appropriate interpretation. Then, of course, in operator algebras, it's important to study the center of an algebra, but also it's important to study the relative commutant of an inclusion, in particular in subfactor theory. So I'd like to study this relative version. So I'd like to start with an inclusion of fusion categories. Just like a subfactor theory, we look at an inclusion of one fusion category into another. Then we look at the kind of relative commutant of the smaller one in the larger one. But so this is like the so this is a kind of a relative commutant, but it's in the sense similar to the above one. So I call it the Drinfeld of the relative. Which can be defined or characterized as follows. And so this also appeared in a recent study of Enriquez where he studies a double commutant of fusion category. So this is a relative version. Then, so again, we have three formulations which are equivalent to each other. So again, we have a construction of the Longo-Rehren subfactor or the asymptotic inclusion, also proper symmetric enveloping algebra. So, but here we use the same algebra. Okay, the same subfactor for C. Sorry. But then we look at more RR bimodules. So here in the previous setting of this Longo-Rehren subfactor, we looked at the RR bimodules arising from that subfactor. But then here we have the same subfactor, so we use more. So we look at okay, this way, iota lambda identity or iota bar, where lambda is in the larger fusion category, and iota is the inclusion map. We look at, so this is a bimodule which canonically arrived from this one, or in the sector language, one is the dual canonical endomorphism. Then look here, if you use the lambda from the smaller fusion category, we get that system. But here we use this larger set of bimodules here. Then we get larger system of bimodules. This is what this is the actually gives the new fusion category, the relative Drinfeld commutant. The second, so everything is parallel to the previous one. The second one is the half-braiding. So basically we have the same kind of thing, but now in the previous setting, sigma was an object of the smaller fusion category, but now we take an object in the larger fusion category. Okay, D is larger, C is the smaller one. And then we have the same relation. And they are in C, simple object in the smaller fusion category. So we have an object in the larger fusion category, but we consider half-braiding with respect to the smaller fusion category. This gives the notion of slightly generalized half-braiding, and then this gives a sorry, not braiding. This is a new fusion category. This is not braided anymore. So this is a new fusion category, which is this concrete one concrete description of C prime intersection with D. So here we have D, but here we have C. Okay. Then the third version is parallel to this one. So again, the cube algebra. Oh, actually, I'm erasing this one. So the same formula, but the different things. So we have again a square where all the four edges are labeled with lambda mu nu, but now lambda and nu are from the larger algebra, larger fusion category, and mu is in the smaller one. So this is in the smaller one. While lambda and nu are from the larger fusion category. And in this way, we can define the product and star structure. So this is a relative cube algebra. So this gives a relative cube algebra, which is also again a finite dimensional C-star algebra. So then here again we look at the minimal central projection or simple command. Then they give the new category. Yeah, minimal central. And following Izumi's work, we can fairly easily prove that these three approaches are mutually equivalent. So in this way, we get a new description and that's the definition of C prime D. Then one remark is that we have a notion of the dimension. So in the fusion category or bimodule, category of bimodules, so each object is a bimodule, so each has a Jones index. Then its square root is the dimension, or it's a dimension of the analog of the statistical dimension in the Doppler-Hager-Overth theory. So we have a dimension. Then dimension C is defined to be the square sum of the dimensions of each simple object. That's a standard definition in the tensor category theory. Then dimension of the quantum double is actually equals to this one. This is well known. So the dimension is squared. Then for this relative version, this is of this thing. This is also fairly easy to see. So we get this kind of thing. Then from this kind of thing, we this is compatible with this this Drinfeld center. So if we take C itself, this is really the usual Drinfeld center or quantum double. So we have this inclusion. This is the fusion subcategory. So my relative Drinfeld commutant contains the usual quantum double, which looks quite natural, but this is not true. Okay. If we look at the relative commutants of algebra in the usual sense, we do have this kind of inclusion, but in this setting, we do not have this one. Okay. Then, so up to this point, everything is completely general, but in a concrete situation, it's difficult to compute the quantum double explicitly, and also it's difficult to compute the relative Drinfeld commutant explicitly for a given thing. But then there is some fairly general setting where we can do such a computation explicitly. That's related to alpha-induction. So I now explain the setting of alpha-induction. So this is rather an old work, originally due to Longo-Rehren, and then Fenshu studied this one in detail. And also with Beckenhauer and Evans, first without me and later with me, we have general study of this alpha-induction. And the setting is the following. So I now change the notation a little bit now and take C to be the modular tensor category. Of say bimodules, say NN bimodules. So this means braided, in particular braided. So X tensor Y is somehow naturally isomorphic to Y tensor X in some systematic compatible way. Then suppose that we have, so if we have a subfactor, so now n is given, and we look for a subfactor or over factor m which contains n with such that this bimodule, so the larger factor regarded as a bimodule over the smaller factor, this is decomposed, this is an object in this T. So this kind of thing is called a Q system or Frobenius algebra or algebra in a tensor category or whatever. So then if we do have such a factor m for a given modular tensor category, or in other words, if we can make up a larger factor m by composing, by adding bimodules in this tensor category, then we have a certain induction machinery. So we have an induction functor which sends an n bimodule to an mn bimodule, which is represented by alpha lambda plus or minus. Here this is plus minus. This depends on the choice and the choice of crossing, braiding. So here we have a braiding, which is a part of the assumption. Then we have notion of over and under crossing, and based on which one we use, we have two different inductions here. So this is like an induction machinery in the classical representation theory. So in the classical representation theory, we have a subgroup and a larger group. And if we have a representation of a subgroup, we can make an induced representation of a larger group. So something like that here. So this is called alpha induction. Then we have some. Here we have the original modular tensor category C, and each dot represents a irreducible bimodule or simple object in the fusion category. Then we can apply alpha induction, alpha positive, alpha plus induction. Then we get some irreducible bimodule. And then we apply alpha minus induction. This is a different thing. So then we if we apply positive induction, we get some, say, finitely many bimodules which make some fusion category. And if we apply the negative induction, we get a different category. And then they generate a larger category. So for example, we multiply this one with this one in the sense of relative tensor product, then we get something new. And then we have something larger. So in this way, we get this kind of different fusion categories. And then we use the notation. Here, this is D plus. D plus is the fusion category of bimodules arriving from positive induction. And D minus is the fusion category arising from the negative induction. And this part, the intersection of these two fusion categories, I mean the objects arising from both positive and negative induction. So this part is D0, and this the entire system is D. That's also a fusion category. So that's a general thing. So then our general result says this.
Plus and divine.
Yeah, generated by both inductions. Yeah, yeah. Then, so in general, what we get is a fusion category, not a braided category. But it turns out that D0 is a braided category. So D0 is actually a modular tensor category. We have braiding, non-degenerate braiding there, but the others are not braided in general. Anyway, we have this kind of inclusion of fusion categories in this, like this. Then a typical example is the following. So this setting is purely general in the setting of subfactor theory, but this kind of thing arises from inclusion of conformal field theory. So today I don't explain much about the conformal field theory, but this kind of modular tensor category is realized, in particular realized from a local conformal net, which is a continuous family of factors on the vacuum Hilbert space. So this is an inclusion of the so-called completely rational, whatever it is. Yes. In such a situation, we automatically get a finite index subfactor here. This is a subfactor inclusion. And in this situation, C is a representation category, or DHL, Doppler-Hagrobat category of the smaller net, and D0 is the DHL. Category of the larger net. This can be proved in a general setting of this one. So both are modular tensor category, but D plus minus, they are fusion categories of so-called soliton vectors. So this is a general setting. So in particular, more concrete example is the following. The easiest non-trivial example is the following famous conformal embedding. And if you are not familiar with this kind of thing, this is a conformal field theory machinery to produce the famous subfactor of Goodman-Dollar-Half-Jones of index 3 plus square root of 3. Then, so this is produces a net of subfactors of this type. And in this case, we have D 0 and D plus minus and D. Okay, also C. I put C here. And here I put number of irreducible, say, bimodule, or number of simple objects. In this case, this is a SU to level 10, so it's linking diagram A11. So we have 11 simple objects here. But here D0 is here for this representation theory, we have 3 irreducible objects. And here it turns out that these soliton sectors, we have 6 of them, and they are labeled by the vertices of the linking diagram E6. This is A11. And here we have, it turns out that we have 12 irreducible bimodules. So this is the one particular example which has been studied by many people quite well. So that's a typical situation. Then, so this is an inclusion of fusion categories. So I'd like to compute the relative Drinfeld commutant of these fusion categories. But before that, I'd like to mention our old work on the computation of the quantum doubles of these fusion categories. Okay. Actually, this was done many years ago, but anyway. So the first thing is this the quantum double of D0, but then D0 is actually already a modular tensor category. And if we apply the quantum double construction to something which is already a modular tensor category, it's just a doubling. So this is the original modular tensor category and the Drinfeld product, exterior product with D0 itself, but opposite. This means the braiding is reversed. Okay, so this is quite easy. Then we look at the quantum double of the soliton sectors. Then this is actually the original modular tensor category, the Drinfeld product with D0 opposite. This is this was our main result in the old days. Then, so we have 3 cases. Then the last one is the quantum double of the largest fusion category D, but then actually this is easy because this largest fusion category is Morita equivalent to the smaller, the original fusion modular tensor category C. So the quantum double of D is isomorphic to the quantum double of C. But the C is already a modular tensor category by assumption. So this is again C tensor C opposite. So this is quite easy. So the first and the third cases are almost trivial, but the second case is the main thing, non-trivial thing. So we had this thing, and for this work, we used half-braiding So we use the half-braiding picture, so we had 3 equivalent ways to look at the quantum double, but here for this work we use the picture based on the half-braiding. So for half-braiding picture, what we need is the so-called relative braiding. Relative braiding between alpha plus induced bimodules and alpha minus induced bimodules. So as I said, if we look at the largest fusion category D, we have no braiding there. But if we just look at alpha plus induced bimodules and alpha minus induced bimodules, then we have a kind of braiding between them. So this is only when we have positive ones and negative ones. So this is why we say relative. But this kind of thing produces a nice half braiding we need. This kind of thing was studied by Beckenhauer-Evans in this setting, and also by Oknian in his graphical setting many years ago. So using this kind of thing, relative braiding produces a nice half braiding in this setting. Then we can write down the explicit thing on the right hand side. Then by counting the dimension of the fusion category, we know that everything is there. So that's basically what we do there. Then the new thing with the relative version. Then, so we have three pairs of inclusion. I mean, we have plus and minus, but plus and minus are basically the same kind of thing. So we have this inclusion, and this inclusion, and also this inclusion. So we have 3 inclusions of fusion categories arising from this, and we'd like to compute the relative Drinfeld commutant for all of the 3 inclusions. Then the first, the easiest, okay, plus or minus is the same. So we have this. First, we look at this inclusion. I just write an answer. This is sorry, plus the smallest one, D plus. Okay. And also D plus D. This is D minus tensor C, and then D 0 to D. Then this is actually D plus with the exterior product with D minus. So this is our new result. And we see that they contain the Drinfeld centers. I mean, for example, this contains the Drinfeld center of D0, D0, D0. Okay. And previously we had an opposite sign, but that's about the braiding. And here we have no braiding structure, so it's just a structure of a fusion category, so we don't have an opposite structure there. So this is the thing. And then again, the method is the use of half-braiding. But okay, before this, I should say that the original method of Okinian Izumi for the proof of this identity in the setting of say half-braiding or the tube algebra, then the method is that here we use something like alpha induction, but we use an extension of from M tensor M opposite to the larger algebra R. There is an extension using half-braiding of this kind of thing, so which is quite close to alpha induction. And then using similar method, using relative braiding or half-braiding, auxiliary relative. Produces which way first and the second. Then the third one is a little bit more complicated or subtle. Okay. Yeah. So yeah, this similar method basically to use for the half braiding we use an extension of the lambda tensor identity, but now just by using a lambda tensor mu opposite and then by extending them we can produce all necessary RR bimodules or endomorphism. Actually, in this setting, we use the endomorphism picture, the sector machinery of Longo. And then the case 3, D0 relative commutant in D, that's a little bit more complicated. Because there is if we want to apply this machinery directly to the setting of 3, there is some small technical problem. Then we have to instead look at quantum 6J symbols. So quantum 6J symbols are of this kind of thing. So this is a picture where we have no incoming or no outgoing arrows. So here we have 4 triple points. So this is basically a composition of these 4 intertwiners in some appropriate way, and this is a complex number. So and we have 6 edges. Yeah, 6 wires labeled by 6 bimodules, and this is why we say 6 here. So this is a complex number. And this is basically like a connection which describes the commuting square in the subfactor setting. So this gives a complete description of your unitary fusion category. Then in this setting, we look at 6J symbols. Then we have this kind of thing. And it's difficult to write, but we have something. So we have doubling of everything. So this is the original. And this is a kind of doubling. And actually, one is for d plus and one is for d minus. And using this kind of thing, we can identify the 6J symbols of the relative Drinfeld center here. Then it turns out that this really produces a Drin product of, so one copy produces d plus and another copy produces d minus. So this is the way it is. Then, for example, in this situation, we have this. So this has 3 simple objects, and this has 12 simple objects, and this has 6 times 6, so 36 simple objects. Okay, I stop here. Thank you very much.
Questions, comments?
Yeah.
Are these commutant related to something like defects or boundary conditions? So
I think so, but
besides the mathematical motivation you mentioned, was this?
yeah, it's related, but I'm not sure of the exact relation now. Yeah, there must be. Yeah, actually, I was vaguely motivated by that kind of thing, but not directly.
Comments? There is no, then let's.
Okay, thank you.
So the next talk will start at